In this video, we will introduce our paper, FedWSQ, Efficient Federated Learning with Weight Standardization and Distribution-Aware Non-Uniform Quantization. Federated learning, or FL, is a decentralized paradigm where multiple clients collaboratively train a global model without sharing raw data. Clients train on private datasets and only send local model parameter to the central server, which aggregates them into a global model. Furthermore, FL allows many clients to participate asynchronously, enabling continual model updates with fresh data generated on-device. However, real-world FL faces critical challenges. First, data heterogeneity, where each client holds data from different distributions, which can lead to inconsistent updates and slow or unstable convergence. Second, partial client participation, where a small subset of clients participate in each round due to resource constraints or connectivity issues. Finally, communication bottlenecks, where frequent exchange of large models is impractical over low bandwidth or energy-constrained networks. These challenges worsen local gradient divergence, slow down the global model convergence, and ultimately degrade FL performance in real-world applications. To address these challenges, we propose FedWSQ. It combines weight standardization, WS, with our proposed Distribution-Aware Non-Uniform Quantization, DANUQ, to improve both learning stability and communication efficiency. Here we explain how WS contributes to stability. Typically, local updates on heterogeneous data cause client drift. WS addresses this by projecting out two-bias DC component and local parameter direction. This aligns local updates more closely with the global direction, yielding smoother optimization and better generalization under heterogeneity. After applying WS to convolutional or linear layers, each client obtains local model parameter updates. These updates are still in full precision, which makes communication costly. So, before uploading to the server, we need to quantize them efficiently. Here we analyze the distribution of local model parameter updates. The histograms on the right present empirical results from our experiments. As you can see, the distribution closely follows a standard normal distribution curve. DANUQ leverages this property by placing quantization levels adaptively, thereby achieving higher efficiency than uniform quantization. To design the optimal quantization levels, we model the updates with a standard normal distribution. Our objective is to minimize the quantization error under this distribution, which is formulated by the equation shown here. This optimization yields the pre-calculated non-uniform quantization levels for 1, 2, and 4-bit, as listed on the right. Now, let me explain how these quantization levels are applied in practice within our framework. After training, the local model parameter updates are converted into a B-bit representation using global scaling vectors and carefully designed quantization levels. This is our DANUQ. Each client transmits both the quantized parameters and its scaling vector to the server. This guarantees reduced communication cost while preserving local model update values. Next, we explain mixed channel bit allocation. This strategy enhances communication efficiency by balancing update quality and transmission cost. In the fixed bit allocation, FBA, each client keeps a constant bit width throughout training. In contrast, in dynamic bit allocation, DBA, each client is randomly assigned a bit width at every communication round. Both approaches average out to about 2.33 bits per parameter, offering a good trade-off between accuracy and efficiency. On the server side, the updates are dequantized back to higher precision and aggregated to refresh the global model parameters. Importantly, the global scaling vectors are reused across clients, ensuring consistent scaling during training. Before presenting the results, here is the experimental setup. The key variable is the Dirichlet parameter alpha, which controls the level of data heterogeneity across clients. When alpha is lower, such as 0.1, the client data is highly skewed, creating a very challenging non-IID scenario. In contrast, larger values like 0.6 and IID case correspond to more homogeneous distribution. With this setup in mind, let's now look at the results. First, we compare our method against state-of-the-art baselines. Across all benchmark datasets, FedWSQ significantly outperforms classical FL methods such as FedAverage and FedProx, and even surpasses strong baselines like FedRCL and FedACG. Notably, even with 4 or 1-bit quantization, FedWSQ outperforms other quantized FL methods like FedPAQ and FedHQ+, and remains robust under both FBA and DBA configurations, averaging about 2.3 bits per parameter. Second, we compare RDANUQ with uniform quantization, UQ, both with and without WS. Across all datasets, alpha and bit widths, DA and UQ consistently surpasses UQ. Moreover, WS and DA and UQ are complementary. Their combination delivers the most robust FL performance, even at low bit rates. Next, we compared to other non-uniform quantization. NF and FP collapse under severe heterogeneity, especially at 1 bit. In contrast, DANUQ consistently outperforms both across all conditions. Finally, we analyze the loss landscape. Prior methods show sharper or unstable surfaces, while FedWSQ yields a flatter, more stable basin, indicating better generalization. For all architectures, FedWS and FedWSQ significantly improves accuracy over the vanilla model. In conclusion, WS effectively mitigates the client drift, accelerating convergence and generalization under difficult FL conditions. DANUQ significantly reduces communication overhead without noticeable performance degradation. Extensive experiments show that FedWSQ consistently outperforms state-of-the-art FL methods, even in a highly heterogeneous data setting. Thank you for your attention. Please refer to the paper for additional experiments and ablations. Paper and code are available via the QR codes or the links below.